So find the exact solution of sine squared x minus 3 over 4 equals 0. So first of all, I want to solve for the sine. So I'm going to algebraically rearrange this. So this is sine squared x equals 3 over 4. I'm going to square root both sides of this, and I'm going to get sine x equals plus minus square root 3 over 2. Okay, so I need to draw that sine ratio in the circle. So now there are going to be, so I'm going to break this up. So the sine theta, or sine x, equals root 3 over 2. That's going to be in quadrants 1 and quadrant 2. Okay, this happens to be a special angle as well. So this is going to be root 3, 2, positive root 3 there. So we have two different angles. We'll call that one theta 1, and this one here we're going to call theta 2. So we also have sine x equals negative root 3 over 2. That means it's going to be in quadrant 3 and quadrant 4. Okay, so we're going to call this one here theta 3, and the one here, the last one we'll call theta 4. Okay, so solving for x, since this is an exact value problem, we know that we have all the positions in the circle from 0 to 2 pi. So being an exact value, this is a 30-60 triangle, and so that's going to be 60 degrees, or in pi over 3 in quadrant 1. For quadrant 2, it's going to be 2 pi over 3. For quadrant 3, it's going to be 240 degrees, or 4 pi over 3. And then quadrant 4 angle is going to be 5 pi over 3. And we can do this without a calculator because root 3 over 2 is a special angle ratio. So this represents one full period of solutions. Okay, so if we had different periods, we can adjust our solutions based on the different periods. But in this case, it only asks for 0 to 2 pi, which represents one period of that sine function. So this question says, explain what's happening to the arc length on a unit circle as the sine, compared to the sine ratio length on the unit circle, as the angle gets smaller. So I'm just going to sketch in this diagram of a unit circle here. And we know that in a unit circle, the arc length is this length here, and the sine ratio is going to be this length here. Okay, so there's my sine theta, and this arc length represents theta. And those lengths aren't that close in length. They're relatively close in length, but they're not that close in length. But as we make it smaller and smaller, so as we make the angle smaller, so I'm just going to sketch a different picture here. So a really small theta, what ends up happening is this curved length and this straight line length here become closer and closer. So as we make the angle smaller and narrower, we kind of start zooming into the curve, and the more we zoom into the curve, the more straight it looks. And in fact, the sine value starts to match the theta value. So what ends up happening is, we write it this way, the limit as theta goes to 0, we could say that the theta value, so the ratio of theta over sine theta that ratio starts to become close to 1. So as theta approaches 0, that value approaches a value of 1. So the ratio is a 1-to-1 ratio. So this is an important concept in calculus. So in fact, this is an identity that we use later on in calculus. We could do the same thing for cosine, but the cosine is a little bit different because we're comparing the horizontal value cos to the arc value x. So in this case here, we would have to kind of estimate. So if I draw it here, I can see that x is definitely longer than cos, but if I want them to be approximately the same, I can sketch another diagram here. And to make the horizontal value similar to the arc value, it's probably going to be somewhere around here, close to 45 degrees. Okay, so this value here, the cosine value in this picture, is more similar in length to the arc length x here. Okay, so again, we're just kind of estimating. This would be very hard to do as an exact value, but if we were to estimate maybe something that looks like this, it looks like 45 degrees is not a bad estimate. It's probably a little bit less than 45 degrees though.